Okay, so last time, again, we were working in section P5, and I want to finish that up today. So I figured it'd be good to do some examples with addition and subtraction of them, and then I'll let everyone try one on their own. Okay, should be good. Okay, so this is just a reminder. It's just like with adding fractions, remember, okay? Just like with adding fractions, you want to make sure the denominators are the same, right? You can only add and subtract fractions, rational numbers, fractions of integers, that is, when the denominators are the same. So you need a common denominator. And we talked about the LCD. We did actually talk about that on Wednesday, if I remember correctly. We have done that, okay? And, again, that's really the best choice for the denominator, mostly because at the end, you're going to have the least amount of simplifying to do. I mean, theoretically, you can use any denominator you want. But again, the least common denominator will be the best since you'll have the least amount of simplifying to do. Now, from here, this is just a reminder. Once you know what that least common denominator is, and you want the denominator to be that LCD, basically you're going to use this to get that. In other words, you're just going to use this rule so that your fractions have the same denominator. You're going to multiply the denominator by whatever's missing, and whatever you do to the bottom, you do to the top. That's all. Again, you can't just, multiply by the bottom and not by the top because you want everything to be algebraically the same. Okay. And here, of course, B and C are non-zero. That kind of goes without saying. Well, yeah. And once the denominators are the same, just like with fractions of integers, you add and subtract by adding and subtracting the numerators only, and the denominator you leave alone. Okay, so here's an example. So here, of course, you can't just add and subtract the numerators. In the textbook, they have those examples, but I figured it'd be better to do this. So here, we got to get the denominators to be the same, right? They're different. Okay, well, remember, to get the LCD, we factor. I mean, it's a little bit easier here because these are already factored, as you can see. Okay. So we list each factor, right? That's what I'm doing in this little table. We also list their greatest exponent, right? Among these denominators, you list the exponent, the greatest exponent, the biggest one that is, of each factor. And here, of course, in both cases, for both factors, the greatest exponent is just 1. In fact, that's the only exponent. So the least common denominator, it's just x minus 1 times 3x plus 2. That's all. I wrote it to the first, but again, when the exponent is 1, we don't write it. Okay. So now that we know what the LCD is, we're going to use that rule that was on this slide, right? We're going to use this rule a bunch of times. Namely, what we're going to do is we want the denominator to be this. So what do? We got to multiply this denominator by x minus 1. And again, whatever we do to the bottom, we do to the top. You have to keep it balanced, algebraically equivalent. So from here, we get this. Same thing with the other expression, right? With this one. What's missing here? To get the LCD, we're missing 3x plus 2. So what do? We multiply the denominator by it. And whatever we do to the bottom, we do to the top. And so we get this. Okay. All right, so now the denominators are the same. So now we're able to add. Okay, I was just checking the title. I forgot to change the title of this, but that's easy to fix. Anyway, so we add, as you can see, right? We're adding, this is what we have over here. We're just adding them together. And when we add the numerators, right? I've seen students make the mistake where they add the denominators as well. You don't do that, okay? So from here, well, we're going to get this. Notice I missed a step. From here, we get this. And notice that we FOIL, right? We have to multiply, because again, we're not done. We want to simplify this. So we have to FOIL this. So we have here 9x plus 6 minus 3x squared minus 2x. See, I'm just FOILing it. And now we add by combining like terms. And when you do that, you get this. You actually get this here, but what I did was I rewrote it this way, as you can see. But now we want to simplify this. Okay. Now we could try factoring the numerator, but we really don't have to. And why don't we have to? Well, it's really enough to determine if x minus 1 and 3x plus 2, if they are factors of the numerator. So, we could factor, but it's really by the factor theorem, we don't have to, right? What we can do is if I let capital F of x be the numerator, it's enough to evaluate capital F of x, the numerator that is, at 1 and at negative 2 over 3. Remember, to use the factor theorem, the coefficient of x has to be 1 and it has to be x minus something. And that's what I'm doing here. That's why I went from here to here. I know it's tempting to just say, oh, well, let's just check f of negative 2. Well, no, you have to be in the right form, so to say. The factor theorem, remember, it has to be, the coefficient of x has to be 1, and it has to be x minus something. Okay, that's good. So from here, let's do that. I did f of negative 2 over 3 first, right? That's what we get here. And if you plug it in, this is what we're doing. As you can see, I am doing a few more steps here than necessary. I guess you probably could use a calculator and use decimals. I did write it in terms of fractions, and I got a common denominator. Basically, what happens is the main point is that we don't get 0. So if we don't get 0, this here, right, is not a factor of the numerator. Okay, what about x minus 1? Well, if you do f of 1, same thing. Well, same idea, not the same exact calculation, but you don't get 0. That's the point. Hence, the numerator does not have x minus 1 as a factor either. So in other words, the numerator does not have either of these as factors, so this is simplified. Okay, so we're good. You could try factoring the numerator. It's not easy to, I don't remember, you probably could try the AC method. You can also see, no, that's right. All right, so basically by the factor theorem, we're good. Any questions on this one? All right, next one then. So here's the same idea. The only difference now is that we're going to subtract. But again, we need a common denominator. I did email the notes, so you do have the notes in front of you. So here we have these two. Now, it's always good to factor the denominators, okay? Sometimes they're already factored, like in the first example. Here, x minus 5, you can't factor that down any further. X squared minus 25, right? You can factor that. We have seen that. You know, it's a difference of two squares. So we factor it, as you can see. So now we have these two. What's the LCD? Well, here, as you can see, the factors are x minus 5 and x plus 5. Here we have x minus 5. So we list the factors. We have x minus 5 and x plus 5. Okay, we don't list x minus 5 more than once. And what are their biggest exponents? Well, among the denominators, x minus 5 only has the exponent 1. X plus 5 only has the exponent 1. So just like the previous example, the LCD is just the product. Okay, so this one's pretty cool, pretty nice that is, right? Because this one here, right, the first term here, the first rational expression, the denominator is already the LCD. This, however, we have to manipulate. No big deal, right? We can see what's missing here. Well, we want the denominator to be this, x minus 5 times x plus 5. We have the x minus 5, so we must multiply the bottom, the denominator, by x plus 5. And we do the same thing to the top.